is Al Ray. I'm the co-lead for the NHD, and this is our advisory call. And today we have two topics. The first one, Matt Baker is going to talk about some work they're doing in the Chesapeake Bay. He's with the University of Maryland, Baltimore County. Is that right?
Yes.
Okay. And then after Matt's presentation, Tatiana Damasio is going to give us a quick update on some changes to the markup tool that have been made recently. So she'll give us an update on that. The majority of the call, though, is going to be dedicated to this Chesapeake Bay elevation-derived hydrography project that Matt's going to tell us about next. So Matt, can you, wait a sec. Before you share your screen, I just wanted to do a quick plug for NHD Plus high resolution and show you the status. We've been making good progress here. Most of the continental U.S. is done now. We're still working on the lower Mississippi and California, and we were beginning work on Region 4, the Great Lakes. There's some complicating factors there, given that almost half the drainage is in Canada, and we have quite a bit of work to do to deal with that side of the Great Lakes. But we're making progress and got quite a bit done. Also, I'll note up in Alaska, we've done one large area called the Matsu pilot project, and we're also working on an adjacent area called the Cook Inlet, and that's in work right now. So Matt, could you go ahead and share your screen, and we'll let you get started.
Hear me okay?
Yes, so Matt, just before you get started, I'm going to mute all and unmute you. Okay, so hopefully this will go smoothly and you'll be able to talk. Just hang on just a second and we'll test that. Now I've got to find your name in the list again. It moved. Okay. Okay, Matt, I think you're unmuted now. Can you speak?
Yes.
Okay, great. Great, I can hear you. Go right ahead, thanks.
Well, thank you for having me here. I'm going to share with you some work that we've been doing over the last year and a half here in the Chesapeake Bay watershed with the goal of deriving high resolution hydrography from elevation data sets. This is basically what I'm going to do today. I'll give you a little bit of background about the project, about some of the field data we collected, what we've been doing to detect channels and the general workflow of our algorithm and how that is used to develop network data sets, and then some of the rather unusual attributes that we were able to generate from this process. One of the motivations for this work comes from just the awareness of the importance of headwater streams and the connection of a number of different hydrologic processes that are related to them. This is from a paper by Brian McGlynn and Jan Siebert from 2003 in the Mai watershed in New Zealand. And what they're doing here is relating the patterns of catchment area in this top left panel to riparian width. And this inset is log scale, so you can see the wider the widths are associated with larger catchment areas. This is a cumulative frequency distribution of the hill slope area of the catchment and the riparian area. And what it highlights is that most of the hill slope area is originating and entering the channel at with very low catchment sizes, whereas the riparian area takes much longer and larger watersheds to accumulate. These 4 panels up here are just showing the network that they were working in. This is the local area, hill slope area contribution, or the specific catchment area to the stream. And this just basically showing a distribution of catchment areas entering the stream throughout the watershed. Here is the width of the riparian zone, with the green indicating a broader width along the larger order system. And the take-home message, I think, is in this bottom right-hand panel, which is the ratio of the local riparian width to the hill slope area. And here what you're seeing is that the darker colors are places where the riparian zone or the alluvial aquifer is really small relative to the amount of hill slope area that's entering the stream at that location. And this highlights the role and the high level of connectivity between the hill slope and those zero order catchments in many cases, and the landscape. So there's a need for higher order stream maps that is broadly recognized, and I think this group knows better than most. These maps are important for recording the current status of stream channels throughout the United States and future change. It's important for quantifying stream miles and hydraulic geometry of channels, understanding hydrology through channel hill slope processes, water quality characteristics of streams, and the importance in the Chesapeake Bay in particular of riparian buffers and whether they are being successful as a restoration tool. They're also useful for understanding patterns of channel networks and the architecture of watersheds through discharge accrual or habitat for aquatic organisms and metapopulations. A key aspect of knowing where the streams are is being able to locate and identify opportunities for restoration, and we think that some of the attributes that come along with this data set might contribute to that. But all throughout this project, it's going to be useful to have an objective and uniform product, such as produced by the NHD, over quite broad landscapes to facilitate comparison. So in the graph here, I just am illustrating the importance of having high-resolution stream maps for understanding the transport of a pollutant from some source area to a stream. In this data set, we were very interested in being able to map streams across very different physiographic contexts and land use contexts. So we stratified our sampling protocol by physiographic province. The Chesapeake Bay includes a number of physiographic provinces. The coastal plain in red here, the dark green is the Piedmont, the Blue Ridge is in this gold color or orange, and then the Appalachian Mountain region, Ridge and Valley, and then the Appalachian Plateau, the glaciated portion of the Chesapeake Bay watershed. The project we were initially funded by was a one-year project to develop automated techniques for delineating stream channels. And we incorporated this field sampling approach into this one-year project. So we wanted to go to as many places as we could over a broad range of both physiographies and land uses. So we looked in each province as much as possible for examples of forested catchments, agricultural catchments, and urban catchments. This area also includes a range of LiDAR quality, and we wanted to understand how well any method that we use performed across different resolutions and ages of LiDAR. And in each location on this map, we chose a local area, walked up all of the stream networks in that area, located and photographed stream heads. And altogether, we were able to collect 148 observations within just a few months. That constitutes the field data set that I will present later when I'm talking about the results of our initial analysis. At the present time, we have completed that one-year project and are now in the process of developing high-resolution maps for as much of the Chesapeake Bay watershed as possible over the next 5 to 6 years. So we're in a pilot phase now, identifying several local HUCs where there's already high-resolution mapping going on to sort of demonstrate the utility of our product. So this is the kind of thing that the field mapping effort was able to identify. On the left panel, you can see sort of a wash head where you have very mild banks, but cleaned off soil where the stream starts to concentrate flow. Here we have a much more distinct topographic head with a boulder sitting in it. And on the right, you see a seep and a spring entering in a larger channel with a very short stub-like stream. We also identified channels in very different land use contexts. Here's one with a root wad in a sort of mixed land use watershed where there's seepage flow underneath and coming out to form a much more well-defined channel. Here's a lawn and someone's backyard with a drainage pipe creating a head and a flow with some riprap around it. And here is a storm sewer discharging right into what was a hollow and is now a highly incised stream. And I wanted to use these photographs to underscore the real effect that humans have in creating stream heads in places where there's been a lot of human activity, and that's most everywhere. And that is in stark contrast to a lot of the methods that have been developed, which are really theoretical and focused on natural processes. One of the primary ways that most folks approach delineating streams from DEM data or elevation data is using specific catchment area or a threshold of drainage area in order to determine where a stream starts and hill slope processes end. This is a very old technique. I don't mean to imply that it was invented in 2008, but it's still in widespread use today. And it makes rational sense because it's a process-based technique. The problem with it is that it does not include all of the processes that contribute to stream formation or channel formation, and it does not include all of the mechanisms by which channels form. In the late 80s and early 90s, geomorphologists were interested in augmenting straight up aerial-based approaches, and so Dave Montgomery and Bill Dietrich suggested that integration of local slope with catchment area would improve this process. And what they described was a pattern of increasing drainage area with local slope that over the course of a watershed generates a pattern that looks like this with a scatter of different elevation values with contributing area per contour length and local slope. And if those contributing area values were bin, then this pattern sort of emerged. And what was characteristic, regardless of the physiographic region in which this analysis was performed, was initial patterns of increasing slope with contributing area at the margins of the watershed, the headwaters, and then an increasing slope thereafter. And what the investigators were finding was that where channels formed, there was another break in slope, a sort of a secondary break in slope, and sometimes it was more obvious than others. And so they were performing this primarily in the Tennessee Valley watershed just north of San Francisco. And they found great success in replicating field map channels with a threshold-based approach that incorporated both local slope and contributing area. This theory was developed further to describe what they called process domains. So that the idea here is that these patterns of contributing area and slope result from a long-term evolution of the landscape undergoing weathering and uplift simultaneously, and that the stream is both, and the channel formation is both a shaper of the landscape and a direct result of the configuration of the landscape that it produces. They also identified distinct components of the landscape that contribute, that have different morphologies because they are driven by distinct geomorphic processes. And among these is the channel itself, as well as the unchannelized valley, and then the hill slopes that contribute to it. In practice, however, this type of technique tends to be fairly limited in its application, and that's because of the example I'm showing here on the right. Here is an example from Brazil where there's a couple of sets of catchments, and what we've done here is highlighted every different zone or process domain that was identified with this technique. So here we have in region 1 is the headwater catchment, or portions of the catchment. You can see them highlighted in black here. And as one moves up in contributing area and starts to see places that where slope decreases with increasing catchment area, these are sort of like the hill slopes. And then region 3 is supposed to be the unchannelized valleys, and then region 4, the channels. But even this example, which is in a very local area, shows some really stark differences between the catchments and their process domains on this side of the valley and the process domains on this side of the valley. And largely in this particular study, that results from the past history of human occupation on that landscape. And that underscores the idea that these methods are really well developed for natural landscapes, but when there's human occupation and manipulation of terrain, these same techniques don't apply everywhere. It's more of a one-size-fits-all approach. There we go. So contributing area methods ignore alternative mechanisms for generating channels, and that's a long-standing and well-known problem. Here's just an accumulated area map where the red has the higher values, orange intermediate, and green lower. And it's really unclear, although it's clear that the red areas are largely channels, where those channels might begin. And this is a problem that is confronting most folks when they try to delineate stream networks from elevation data. There are places that have fairly distinct valleys and channel features that are observable in the LiDAR terrain, and there are places that are where those patterns are less distinct, but in either case, there are both channels developed in those areas and areas where there's an apparent accumulation of flow that looks like there's more dispersion going on than concentration. And all of these are challenges for delineating a stream network using an accumulation-based approach. More recently, and even a long time ago, investigators used a direct detection approach, and this is what has been favored recently in the literature. As long ago as 1975, local measures of curvature were used to find channel-like depressions as sort of the upper end of accumulation-based processes. And more recently, investigators have used a local terrain curvature, principally tangential curvature or planform curvature, to identify stream heads or channel-like features and other depressions in the landscape as sort of the upper end of these accumulation thresholds. The advantage of this approach is that it detects features that are channels and does not rely on any arbitrary, even if objective, threshold for contributing area. The disadvantage of this technique is that it finds things that are not necessarily streams and can include those in the network as well. The other problem is that these are local techniques and they only consider the surrounding 8 pixels for understanding whether a pixel is in a depression or not. In 2002, an alternative to this type of approach was developed by Yokoyama et al. And this eventually was used as one of the contributing methods to detect streams on Mars. The approach is based on concepts of computer vision and line of sight from any particular point on the terrain. And so this figure here on the right illustrates those patterns. This just shows what is called positive openness, the openness of the terrain around any particular point. And these two, the left-hand columns here show a large angle of positive openness, indicating a local peak, and here is a narrow or low score of positive openness, indicating that there is topographic enclosure of this point. By contrast, negative openness does the same thing, but from underneath the landscape. So in this case, a depression would have a very broad angle of negative openness because it's being examined from below as opposed to above. So the advantage to topographic openness is that it involves a self-adapting window, considering terrain from multiple different distances, and then finding the point on each of these transects that constrains the line of sight. And as a result, the algorithm better identifies features where that enclose a point on the landscape from different distances in different directions. So in practice, these are some figures from Dan Jones's thesis and some work that he's done, and he is, I think, on this call somewhere. But anyway, this is describing that openness technique, showing the enclosure from the zenith angles as well as the nadir angles, and how it can be used to identify stream channels in a terrain. But then the same problem comes when you get to the head, where it's not exactly clear where a cutoff needs to be drawn to find the slope angle that precisely identifies the channel head. Typically, what is done in more recent publications listed below is that there is a threshold value that is determined from either curvature or openness to delineate the upper headward location of a channel, and then from there routing downstream to develop what they call a channel skeleton. So the threshold that is most commonly used is just a QQ normal plot to essentially analyze for breaks from that normal distribution within a particular process domain. The idea is that any measure of a depression is going to diverge from normal if you're talking about channels, because they are unusually shaped depressions in any terrain. So there would be some kind of threshold on this fit of a QQ normal plot, which would give you a value of either curvature or openness that would determine where the heads were located in the stream. And this approach typically works fairly well in natural landscapes, but it's sensitive to topographic analyses associated with human activity or anomalies. So as an example, I wanted to show you what this might look like in real terrain. Here's a terrain with a gravel pit in it, so it's got some very steep slopes. And this is a threshold-based delineation of depressions in the landscape. And you can see it's really good at identifying those depressions associated with the gravel pit. And because of that man-made feature in the landscape, that kind of regional threshold doesn't do a good job identifying other depressions in the landscape. On the other hand, a non-threshold based technique is less sensitive to the man-made depression and is able to identify channels throughout the landscape. So in our approach, we were very interested in identifying some method that would not involve any kind of threshold-based technique for delineating depressions. What we ended up settling on is a technique called geomorphons. It involves and integrates both positive and negative openness, so it takes advantage of that variable search radius for detecting depressions. And the way it works can be described up in this top right-hand corner. Here's that same kind of multi-directional search radius, and at every point along each transect away from any point in the landscape, the algorithm is identifying features that are higher than the focal pixel, features that are lower than the focal pixel, or even with the focal pixel. And based on the relative elevation of all 8 points in all directions around any particular location, the algorithm classifies it into one of the 10 ternary forms that are described here as elevation, as little cartoons. So there are 10 major forms that result from 45 general combinations of different numbers of transects that are higher or lower than the pixel of interest. And that's also represented by these color-coded points around every focal pixel here. We were principally interested in valley features and hollow features for this analysis. The advantage here is that it's robust in its processing, it's relatively rapid in how fast it can classify the landscape and objective. There are very few input parameters, but there are many different pieces of information that are produced along with the classification of ternary forms. So geomorphon analyses tessellates and classifies the entire landscape. So if you're looking at a landscape, you would get something that looks like this. And here you can see the encoding of the landforms. I'm going to be, oops, I'm going to be looking primarily at the dark blue features here, to some degree, maybe the lighter green features. Those are the valley landforms. But whether it's actually a valley or not depends on the scale of the search radius. So here, just an example of different search radiuses and the output that they produce. And what you can see is that different size features are delineated using different scale search radiuses. These are finding the maximum signal that constrains line of sight within that search radius. A key insight that we had when we were working with geomorphons was that we can manipulate that search parameter for different objectives. In our case, we are interested in delineating valley domains from the much more narrowly focused channel domains. So our approach involves using geomorphons to delineate valleys that are much broader in terms of their process domains, much broader in terms of the search radius. We actually skip over the initial landscape next to every cell and only focus on changes in terrain that occur at much broader distances from any focal pixel. This allows us to delineate sort of the valley context for our mapping effort, and allows us to interpret depressions that are more likely or less likely to be channel-like features. When we do this kind of delineation, we can actually develop a network from the valleys themselves and ensure that they are contiguous with the 1 to 24,000 NHD. And as a result, we don't go back over places that we have already been mapped as streams. We focus primarily on headwater locations upslope from the headward locations of the NHD. Then at a much finer resolution or search radius, we identify channel features using high-resolution DEMs, principally LiDAR DEMs. And it's actually the evaluation of both of these products in connection with one another that allows us to filter some of the channel-like features identified in this high-resolution map and map stream channels. So this is just an illustration of the way our process works. We start with LiDAR elevation. We actually classify the terrain using the valley parameters, the search parameters, at a 10-meter resolution. This is upgraded LiDAR data. And that produces a tessellated landscape. We focus on the blue areas here. Those are the valley features, and isolate those. And then we reclassify the terrain with the LiDAR data using a much narrower search radius and produce the channel map. And that, again, we're focusing primarily on the blue areas here. We could also consider, in certain circumstances, the light green areas. Those are what are called hollows. And we can extract channels as those valleys that are contiguous with the valley network. And that includes everything that is contained by the valley network here, as well as those features that are outside of the valley network but touching. And you can see that this is clearly a channel-like feature or a gully, and it gets included in the map. Here's one where there's a little bit of discontinuity in the elevation data, maybe because of a road going right here or the edge of a field, and as a result, it gets cut off. There are discontinuities within the channel skeleton. That's the red area that we're identifying here, and we return to those later. One of the aspects of this process that we found to be useful is to perform a little bit of denoising on the DEM data. In this case, we're using an edge-preserving filter that separates or attempts to separate signal from noise in the DEM. But unlike smoothing, it doesn't relocate the terrain features. It keeps them where they are. But the output tends to be aesthetically pleasing and, probably more importantly, creates greater continuity along the channel skeleton for improved processing results. This isn't necessary, but often helpful, and sometimes we do both in our effort. In the comparison that we ran in our first year of analysis, we compared a number of these direct detection techniques. We used planform curvature to define depressions. We used negative openness, positive openness, and a combination of those openness values we developed ourselves. And then we used several geomorphon approaches. For all of the methods above here, they were filtered by the size or scale of the depressions that were identified, and also whether they were downstream along a streamline from other identified depressions. And that's using a flow direction surface. And so that's what we're calling a routing filter. And that eliminates some that don't fall directly on a high drainage area accumulation line. For the geomorphon approach, we did that too, but we also employed simply the valley as a filter, the valley maps that we created as a filter for comparison. And that's what I'm going to illustrate here. This shows the number of depressions that are originally detected for curvature, for negative openness, positive openness, geomorphon, and then what happens when we apply these filters in terms of the landscape proportion that is identified as part of the skeleton. So here is a flow accumulation filter applied to curvature, and this is a size filter, making sure that only large accumulations of pixels identified as depressions are retained in the skeleton. And this same approach has been applied to negative openness and the negative openness, positive openness, and geomorphons. And then to the right here are the geomorphons that are filtered only by the valley and then used a size filter. The reason for showing you this is to illustrate the fact that the valley approach for filtering accomplishes almost the same kinds of reductions in the number of disparate pixels that are eliminated from the original depression maps that we make, as would be filtered by some kind of flow accumulation network. Here is just a comparison in terms of the upstream and downstream flow distance routing along a flow direction surface from our observed channel heads for all of the 148 sites in our field sample. What we have here, and this will be true in the next graph too, curvature, negative openness, positive openness, the combination of openness techniques, the geomorphons filtered by routing and size, and the geomorphons filtered by their valley. In each case, I'm showing you box plots, and then the red diamond is the average as opposed to the median. What I want you to notice, first of all, is that most of these methods are designed to essentially err on the side of a not going quite as far as the observed channel head. And that's what we want. We'd much rather have an error of omission than an error of commission where we're making up channels that don't exist. We'd like to limit that as much as possible. The other thing you may notice is there's not a huge difference in terms of the whole distribution of error going across all of these methods. And that's also good. That sort of implies that none of these methods is overly superior to the other, although the processing involved in the geomorphon methods is far less than all of the others. And then finally, you can look at patterns of extreme values by comparing the mean and the median across all these techniques. I guess the take-home message here is that the lowest amount of error is in these middle two categories, but the geomorphon method with the valley filter is sort of comparable to what you get from a curvature method. This one in particular, the combined openness technique, is much more process intensive than the one on the right, and as is this compared to the one on the right, the channel geomorphon versus the valley geomorphon. Now, the next graph is going to be really complicated because we're going to break this out by physiographic, oops, no, this is a table, sorry, the next one is the complicated one. This just gives you a sense, I'm going the wrong way, I have a very sensitive mouse. This just gives you a sense of the overall errors in this data set. So this is the RMSE in terms of the distance up and down the flow surface from the observed channel head. This is the median distance that you saw in the box plot, the mean, standard deviation, the frequency at which an error is omission versus commission. And so remember, we wanted to keep this relatively low, and you can see it's relatively low across the approaches. And what I just want to emphasize here is that the geomorphon methods are essentially equivalent to, maybe a little bit better on an average than most of the other techniques in terms of the types of error that are being generated. Here's that complicated graph, and this just shows that same pattern of error across really different physiographic contexts. And keep in mind that in many of these, we have multiple examples of the physiographic context with different land uses built in. So sometimes that is what contributes to error. So here we have the glaciated part of the Appalachian Plateau. In this landscape, a lot of the streams start in headwater wetlands that don't have a really clear topographic signal, and so we tend to omit some of the heads in this type of landscape, and that's true across all the methods. Here's the Blue Ridge, where we were working primarily on talus slopes like boulder fields, and so a lot of the streams actually started and were flowing underneath the boulder field, and we were unable to detect them with topographic signatures for the most part. Here we are in the intercoastal plain, the outer coastal plain, the Piedmont lowlands and the Piedmont uplands. I don't know if you can see this. I'm going to move this over. Okay. Then this is the Valley and Ridge province, and then a portion of the Valley and Ridge that was in karst terrain. We felt like it was important to understand the errors that were generated in karst terrain as well. And I think the take-home message from this slide is that there are some physiographic situations that produce challenges for any delineation technique that relies on elevation signals. But by and large, the differences across techniques were far smaller than those physiographic differences. And the geomorphon techniques were equivalent to or better than, for the most part, the techniques from other kinds of topographic detection. Here's an example of the kind of problems that occurred in karst terrain, just to give you a sense of this. Here's the delineated channel head. You can see the water flowing right here in the bottom of this picture. This is the location where that photo was taken, the yellow dot where the red arrow is pointing. And this is the terrain around that. And what you can see here is that there's a really clear valley-like feature that even has a hollowed out bottom that our algorithm was interpreting as a channel. On the other hand, that's not where the water was flowing. And so this is where the field technician, David, and my collaborator identified the channel head. Further up, there were other features that looked a little bit like channels, but they would not have been contiguous with the valley feature identified by the broader search algorithm. This slide is reminding me about another problem that arises when one uses, these are depressions identified with a threshold-based technique in red, and then what we've done is just trace downstream what happens, or downslope, what happens if you follow those heads and do not do any kind of topographic correction in the LiDAR. And what you see is that there's a lot of discontinuity in places that have some kind of sink in the landscape. And so any kind of flow correction is going to have to involve hydrologically correcting the topographic variability in LiDAR DEMs. Once these skeletons are detected, most applications then rely on that kind of flow direction process. So it's a cell-to-cell routing and flow tracing from whatever set of filtered pixels is identified downslope. The problem here is that this is a local neighborhood analysis, so it ignores other pieces of information that might be available in the landscape. And often it requires hydrologic enforcement, whether that's sink filling, stream burning, reconditioning, or breaching to allow water to flow off the DEM. And some of the built-in analytical procedures that exist in most of the existing direct detection techniques really slow processing and often require independent validation and error checking. Some of these analytical procedures are kind of listed here. So if you identify depressions with curvature or openness, you have to identify regional thresholds in order to determine what level you're going to use, to set that, what level you're going to use to set the threshold. If you filter those values so that you reduce the number of pixels that are classified as a depression, you have to decide on a size filter, and then you have to perform a downslope routing. That requires all the DEM pre-processing I mentioned earlier. When you trace or route, that requires that pre-processing, and it uses limited information. And that can be a shortcoming and require a lot of extra labor. And then, of course, a lot of these techniques actually use some form of trimming or removal of duplicate drainage lines after the routing occurs. And then finally, there's a network that is developed from some kind of raster-based channel map and flow direction surface. In contrast, The depression and filtering approach in our technique is accomplished by the geomorphon analysis. And as a result, we have a lot of ancillary information that we can use to perform tracing and routing. In fact, this becomes a very simple and small process connecting adjacent patches using a least cost analysis, which I'll describe in a minute. Post-processing is largely unnecessary, and downslope routing can be used to create a linear network. So here are the products that come from the work that we do. The first, when we have a terrain, is what we call the channel skeleton. That's a two-dimensional depiction of channels in the landscape, so groups of pixels that preserves aspects or attributes of widths as well as discontinuities. In our case, we have very high resolution land cover data, 1 meter land cover data that was developed for the Chesapeake Bay watershed, so we can incorporate that to understand the discontinuities that occur, as well as to help with their analysis. We then connect these patches by focusing principally on the areas in between the discontinuities, and we use a least cost path where the cost is set to the elevation to connect these different adjacent groups of pixels. And when we do that, we are able to develop a line work or vectorized line work for the entire network that then we can build into a linear network. We also can add other attributes to this. So this is kind of what it looks like once we do that. And two things are going on here. First, we're crossing road boundaries in a really efficient way. And the other thing that we're doing is moving right along, because we're using the elevation surface as a cost surface, we're moving right along the fall wag of the identified channel, so the lowest point of the channel in any given cross-section. So with these pieces of information, then we can develop attributes of the width of all of these red areas, the channel skeleton, as well as some other characteristics like bank height and flow permanence that we're working on, at least in the Chesapeake Bay watershed. This is the general workflow of the technique. So we employed denoising and filtering, detecting depressions with geomorphon, filtering with the valley geomorphon to develop the channel skeleton, least cost connection of the adjacent groups of pixels, routing and link construction of a channel network, and then attribution of those network features into our hydrologic network, which we expect to be compatible with the kind of data model that is produced by ArcHydro and likely compatible with, or we want to be compatible with, the NHD. In terms of the reach scale attribution, we can convert the sort of pixel width network topology into a stream link grid to be able to develop network properties like stream order. We can summarize the channel areas by width and aggregate them to a link or sublink scale. And we can develop bank height estimates at the same resolution. And that's facilitated by some of the additional geomorphon output. And I'll show you an example of that. In the Chesapeake Bay watershed, we've also developing estimates of flow permanence. I'm not going to spend as much time talking about that, so it's there. If you have questions about it, I can come back to it, but in the interest of time, I'm just going to keep going. So here's an output of the bank height estimates that we're generating. So this is the channel skeleton, but it's color-coded now based on the relative height of the surrounding banks. And I want to point out that that's developed for every single pixel in the channel skeleton. So that means over 100-meter reach, you would have hundreds to thousands of individual observations that then are, different observations that can be aggregated to a distribution and summarized as such. Here, I'm just showing how the color code of this map compares with cross-sections derived from the LiDAR terrain. So each of these black lines represents LiDAR cross-sections, and then you can see patterns of the terrain in cross-section adjacent to each of the locations and see how they match the color coding of the geomorphon output. So in general, just to synthesize what I talked about, we developed a rapid automated method for delineation of channel networks from LiDAR terrain. It still requires some validation and review. We are in the process of doing that, but we think based on the analysis we've done so far that we have something that works faster and produces a quality product than most of the existing techniques. It's useful in the sense that it's, because it uses computer vision, it adapts readily to even human influence terrain. And it focuses on real features in the DEM as opposed to theoretical features or arbitrary thresholds. We saw a lot of variation across physiography and land use, but much more across those types of situations than among methods in terms of detecting the depressions. But we think our routing procedures are an advantage because they avoid things like filling or breaching to achieve connectivity. So we think this kind of approach has some exciting potential for developing new channel attributes and potentially augmenting the efforts to develop high-resolution hydrography. Thank you, and I'll take any questions if folks have them.
Yeah, thanks a lot, Matt. So we're going to modify our plan here a little bit because I think there are going to be quite a few questions. So we will go ahead and take as much time as we need for questions, and I'm going to unmute everyone. So, okay, so you're all unmuted. If you have some questions for Matt, please go ahead and ask.
Hi, Matt. This is Roger, and I'm interested to know if you've selected any of the pilot watersheds yet.
We've been exploring that with our advisory committee through the Chesapeake Bay program grant, and what was recommended to us was that we try to identify pilot locations that were locations where folks were already developing high-resolution data. Those included, and then some other committee members suggested that we just work in places where they were working or other people that had a lot of other data were working, and so that there would be synergy with our efforts. Those were Lancaster County, Pennsylvania, some drainages right around Washington, D.C. I believe that was Cabin John Branch or maybe the Upper Rock Creek, and then some locations in Anne Arundel County, which is to the largely to the east of Washington, D.C. We haven't had that conversation yet. We've been trying to finalize that, but I think it looks to me like one of our first locations is probably going to be in Lancaster County, and then we'll probably move to Rock Creek, and then Anne Arundel County in that order. And then, you know, I think for our grant, we have to do one of those in the first year. I think we'll likely do more than that, but we want to make sure we fulfill the obligation first.
Yeah, that sounds great. I did recommend Lancaster County. So.
Well, you know, there you go. Wise decision.
Hey, Matt, this is Sean Vaughn from Minnesota DNR.
Hi, Sean.
My question is, I'm interested in the 10-meter resolution. How'd you come upon that? I'm assuming that your LiDAR was not collected to that resolution. So is this a, well, tell me why 10 meter, all in there.
Yeah, that's a great question. Initially, we weren't sure how well the valley detection technique was going to work. And so we imagined if we had to do this across the entire Chesapeake Bay watershed that we might delineate the valleys using the 1 meter DEM. But just as an experiment, I suppose, we tried to run the delineation for the 10 meter NED. And we were able to run that for the Chesapeake Bay watershed within a day. And we found that it actually works quite well. And in many cases, works as well as the 1 meter DEM. And since there's not much of a reason to use the 1 meter DEM, we have stuck with it so far. We've explored whether it creates error, and what we found is that in some cases the aggregation to 10 meters does produce some irregularities right around the margin, but in many cases it works just as well. And we found that it's really important that we create that 10 meter DEM by aggregating the LiDAR data. That reduces a lot of the error. But I think either is fine. The most of it's just a historical anachronism of how we explored this process and this method. So, and we have that at 10 meter scale for the watershed.
So then to clarify, part of your validation then, I would hope what you're getting at is you've taken the flow lines and draped them back on top of current imagery, so that the deviations don't go out of the channel that you would see on imagery. Is that the case then?
Well, if you're talking about the valley delineations, we're not worried about that very much. For the line work that we delineate at the channel scale, we are quite interested in terms of validation. We are going to be overlaying it on aerial photographs as part of our validation effort, and looking at how well we are delineating what you would generate if you were mapping streams. We will compare it with other line work, like county level line work, as well as the NHD. When we do that, though, the date of the data set becomes really important, like when the LiDAR was developed and when the stream was mapped. And so it's mostly going to be sort of contemporaneous aerial photography that will form the basis of our validation.
Sure, thank you.
Sure.
Matt, this is Pete Steves. I know you've done some work with roads as collectors and connectors of hydrography. I was wondering if that was built into any of this.
The part of the grant that the Conservancy received, there's different components of it. I'm on one component of it with them, working on the stream mapping component. They're also working on mapping ditches, other forms of drainages. And one of the things that we find very useful is when we perform a channel geomorphon, a channel scale geomorphon, we end up with maps of channel-like features that are not anywhere near a river valley. And what we've been doing is using those as a basis for mapping ditches and other drainage pathways. So we can often find those by virtue of the fact that they're not in a valley, and then identify places that are along roads that might be roadside ditches, or in agricultural contexts that might be agricultural ditches, drainage ditches. And then in some cases we have efforts to drain like floodplain wetlands in glaciated terrain. This happens quite a bit where there's very, very large backwater wetlands in proglacial valleys. And in those cases we they require a different protocol, right? Because they fall within the valley context. Did I answer your question, Pete?
Yep, that was great. Thank you.
Sure.
Okay, so we're almost out of time, but we're going to extend by, say, about 5 minutes or so. We've got time for maybe one or two more questions before we stop.
Hey, Matt, this is Dan.
Dan?
Curious if you guys are planning to compare this method up against, a more comprehensive channel head survey as was done in like the Clarksburg watersheds.
Yes, we'd want to do that. I mean, part of the reason for looking for data sets across the landscape is to find places where folks have collected channel head data, like you have. But also, I know that Julian Jones, for example, Julian Jones? Yeah, I think it's Julian Jones. No. I think it's Julian Jones. I may be remembering his name wrong. Collected data in Virginia for a stream mapping effort a few years ago, and we'd want to try to access that data. And there are a number of Jason Julian, sorry. There are a number of public records that are also available we can use. So, but our purpose here is not necessarily to find channel heads, honestly. It's really to map streams between the channel heads and the existing NHD. So, I mean, ultimately, that's what we'd want to do. So, you know, we or others can continue to refine techniques like this to get to stream heads. But I want to distinguish the purpose of making a high-resolution stream map from actually mapping channel heads with great precision. Does that make sense?
Yeah, thanks.
Sure.
This is Ricardo Lopez. References map.
Go ahead, Ricardo.
I am just asking for references and places where we can look in more detail at the work you've done. Thank you.
Oh, the work hasn't been published yet. The manuscript is in prep. So if you want to learn about our approach, we have a report that we published or gave to the Chesapeake Bay Trust. Send me a request via email, I can send it to you. And then if you look for, there's documentation about geomorphons online. If you just look them up, you'll find the document. And there's a publication by Jasenowitz and Pinsky from 2013 in the journal Geomorphology.
Different sensor. One thing I clean it up for the stuff I have.
If people could try to mute their phones if they're not speaking.
Doesn't matter for the forestry stuff.
Okay, we have time for one more question for Matt before we close.
So he just asked if we'll make sure they're muted.
Hey, Matt, this is Sean Bond, Minnesota again.
Hi.
So I'm really trying to wrap my mind around, I heard you say this wasn't, you're not really striving to map exactly where a channel head is. Yeah, the channel head is typically where we think of as concentrated flow forming to the degree that we're seeing a certain amount of erosion that is captured through LiDAR technology. Yeah.
That's right. I mean, so a channel head feature is a feature that we hope to be able to detect, and in many cases we do, but I guess the purpose of our approach was not necessarily to detect channel heads. The 1-year grant that we got was to develop an approach for developing a high-resolution channel mapping technique. The end goal, I think, would be to be able to generate, to include the heads in that approach, and we get very close much of the time, as you can see. On the other hand, there are many cases where either the LiDAR quality is relatively low and the topographic signal is not very strong, the physiographic contexts that make that challenging, as well as even with high resolution LiDAR, there are all kinds of situations that can mask the topographic feature. So if you're talking about whether we're mapping, we're trying to get as close as we can to the feature that you can see in the LiDAR hillshade, I think the answer is yes, that's what we're trying to do. And we'd like to be able to detect features that are even slightly upstream of that. In some cases, we're able to do that. But I don't think that's a greatest measure of this kind of approach. Right now, I think the greatest measure is developing a uniform and objective process that works across lots of different terrain and identifies things that we're sure are channels, and where there's uncertainty about whether one geomorphologist or another would call it a channel, I don't think that this automated technique needs to wade into that debate.
Yeah, well, that is always a debate, especially with a group like this. You know, the word channel gets all of us thinking about different classifications.
Sure.
Here in Minnesota, I tend to focus on and use language centered around water conveyance landforms, meaning the LiDAR captured signatures of erosion that are induced by the movement of water, and therefore, if it formed and LiDAR captured, therefore it exists, and that becomes our focal point as we try to target point and non-point pollution. So you touched on briefly your interest in going kind of above that channel head, and I guess that's where our interest is as well. And I'll just wait for other information or till you publish something, but I was really interested in that area right around, identifying around the channel head formation, and as well as slightly above, because those are the features that begins to identify where our pollutants and contaminants are first merging in with you know, the first concentrated form of where contaminants are being located on the landscape.
Well, I certainly agree with that, and I think that the nice thing about this approach is that it is not just limited to the requirements or the classification that we've developed, but it can be modified to accommodate other types of fluvial features in the landscape. And I think what you're talking about are the concave portions of the landscape that may not have a channel in them very distinctly, but are areas of flow concentration that, you know, if a local highway or a road goes across and they dump a ditch drainage pipe into the headwater there, it will in size and form an erosion feature, but it may not be that way in a completely forested terrain. And we want to identify those locations, and we do through the use of the geomorphon classification. It's just that we're not using them to make the maps that I'm presenting today.
Sure, understood. And I would guess that experimenting with a less coarse resolution DEM in some of those areas in the upper reaches around and above the head formation might reveal different results as well, because I'm assuming that at a 10-meter resolution, you're losing some of those intricate features of the landscape.
I think you're misunderstanding what we did. I just want to point this out again. We're using 1 meter data. Oops. We're using 1 meter data to delineate the channels. So it's only the valleys that we use the 10-meter data for.
Okay, that's a good clarification then.
Yeah. So really we're talking about something that looks like that for 10-meter data, and then this for the 1 meter data. So much higher resolution. And I think that's really important for finding these headwater locations you're talking about. But you can see even in this map that there are features like this that are mapped as hollows that don't really have a channel associated with them. There's no erosion associated with that particular location in the hillshade.
Right. But yet it
Okay, so
has value.
Yeah, it has value.
I hate to cut it off here, but this has been really interesting, Matt. We've got another call coming right up, actually, on this same line. So we need to end it now. I do really appreciate your joining us, Matt, and sharing this with us. It's really interesting work, and maybe we'll try to get you back. I don't know, in a month or two, or a little longer, a little later, to give us an update on how it's going. It sounds like you've got some publications in the works and so on. So it'd be good to hear back from you. I want to thank you again. And I think we need to close here. Okay, thanks everyone else for joining us. And we'll talk again in a month.
Thank you.
Thank you.
All right, bye-bye.
Bye.
I'm going to end the meeting now.
Okay. Take care, Alan. I appreciate your help.